Alright guys, so in the last class we had started talking about, we talked about properties of some characteristics of flow emerging from linearity. So linear in nature, but these equations are only Navier-Stokes equation or Stokes equation or Kinsey equation. They are valid only and only for continuous phase. They are valid only and only for the phase. Okay, for rigid particles, one can imagine writing down the Newton's law of equation, law of motion. Consequences of Stokes law because of its linearity and because of neglecting del V by del T term are the following: instantaneous, it's linear, it's reversible. Okay, the flow responds almost immediately to forces and reaches steady state or pseudo steady state. If I turn on G, my particle will start settling with terminal velocity. If I turn off G, the particle will stop moving with any velocity. Or if I am applying an external force F, the particle will reach terminal velocity almost instantaneously. And if I stop applying an external force F, the particle will stop almost instantaneously. And we looked at what that instantaneous time scale is. So a time scale much smaller than L by U, or characteristic length by characteristic velocity. So a time scale much less than that is the time over which particle will be accelerating, or del V by del T term is going to be important for the particle at low velocity. Alright, so I have found 4 assignments, so get an idea what kind of time scales we are talking about when I'm talking about, let's say, 10 micron particle, motion of a 10 micron, or settling of a 10 micron particle in a liquid fluid. Then linearity. We looked at how laminar flow is different from low Reynolds number flow or creeping flow or Stokes flow. So in laminar flow, your inertial terms are still important. Even if you are looking at a steady state problem, U dot del U term is important or can be important. For the case of pipe flow, it's not important, or U dot del U term is 0 because velocity and gradient direction, they are connected to each other, so dot product is going to be 0. So it's because of this unidirectional nature of the flow that we didn't have to worry about U dot del U term for a pipe flow. As a result, when you were deriving how pipe flow is going to look like in class, you were able to neglect the entire left-hand side of Navier-Stokes equation. As a result, you were, at the end of the day, essentially solving Stokes flow problem, even though it's not a low Reynolds number. So advantages of linearity: a complicated problem can be divided into number of sub-problems, and some of those smaller problems is equivalent to the complicated problem. I mean, you have to divide the problem smartly to ensure that some of the 3 problems on the right hand side is essentially equal to the problem given on the left hand side. And now, just by looking at the symmetry of these 3 problems, we are able to say that there cannot be any lift force acting on a rigid spherical particle in this case, or in this case, or in this case. And since summation of these 3 problems is equal to the problem on the left hand side, we are able to claim that even in this case there will not be any lift force acting on the particle. When we were looking at just the problem on the left hand side, we were not able to see that. Okay? And this is again only and only possible because of the linearity of Stokes theorem. That you are able to divide more complicated problems into a sum of simpler problems. जो नॉन-लीनियर टर्म अगर इम्पोर्टेंट है तो नहीं कर सकते हैं आप. Am I making sense?
Sir, what is freely rotating sphere mean in the diagram?
Sorry?
Freely rotating sphere.
Freely rotating sphere, like the first problem? Or this problem on the left hand side. So freely rotating sphere is a sphere for which I am not applying any external torque, any external force. मतलब freely rotating means कोई external torque नहीं है. But in this problem, when I'm just freely rotating stationary sphere in a simple shear flow, I'm mentioning stationary, so I am applying an external force to keep it stationary. I am saying freely rotating, the particle is free to rotate if the flow is asking it to rotate.
So that means the sphere is rotating due to the fluid motion.
Yeah.
So then how is the sphere rotating in the first case? The stationary fluid. Rotating sphere is stationary fluid.
So here I am applying an external torque on the particle, which is due to which it's going to rotate. Otherwise, stationary fluid में everything is going to be stationary. And the third feature is reversibility, and we looked at this beautiful example of two cones suspended in these two orientations, and we have an external uniform flow. Uniform flow is constant velocity. Fluid is moving with a constant velocity far away from the particle. The reason I am saying far away from the particle is, on the surface of the particle, of course, the fluid has to follow the no-slip boundary condition. And then in the transition, far away it's constant velocity, on the surface it's zero. In between, the velocity is going to be varying. We'll come on that variation also later in the lecture. But here again, without solving the problem, we were able to say that the drag force acting on both these spheres is going to be exactly the same. The velocity field is again going to be exactly the same in magnitude. And again, the feature, this linearity of Stokes flow. So Stokes flow is essentially an equation or a differential equation. All you need to solve this differential equation is, क्या चाहिए differential equation को solve करने के लिए? Boundary condition. और boundary condition same है तो it really doesn't matter और क्या चल रहा है. Stokes equation, boundary condition. If the boundary condition is same, equation of course is the same, then your solution also is going to be the same. Okay, so a generic statement for a reversible flow. So if UP is the solution of the Stokes equation, satisfying appropriate no-slip conditions on bounding solid surface, then minus U minus P is the solution of the Stokes equation with all external forces and motion of all the boundaries reversed. Possibly by अपना नाम. Guys, please come write your names. Alright, so and this is because of linearity of the problem. Guys, can you take this sheet and write your names there? And please show your iCard when you are doing this. Guys, go to the back and write your names on this sheet of paper that this girl is carrying. Guys, from next time I'll ask you guys to leave the room. Okay? अभी नाम लिख दो उस sheet of paper पे. All right, so just for your information, nowadays our classes are being recorded by the ETSC. ETSC. Yeah, now my classes are going to be available whenever IIT wants to make it available online. They are going to make it available. And when I'm going to ask them, tell me a person who entered the room at 9:14 or 15, they can tell me. Anyway, from next class, guys, I'm going to request you not to enter the room after 9. Or I'll ask you to leave. ये नाम लिखना, I was really expecting 2-4 लोग, लेकिन really better. All right, so guys. So, and this is going to be a tutorial problem on comparing the drag forces acting on these particles. So these are two cubes in uniform flow, two cubes in two different orientations. Okay, and a similar problem you can think for the cones that we were looking at, and now they are also in two different orientations. Earlier they were in one orientation and the other one was in orientation of 180 or was flipped by 180 degrees. Now this is at an angle. Yeah, please recording वगैरह मत करना. It will. You are really lowering the bar if that's what you are involved in. Anyway, so the three sphere problems. So I hope some of these features of Stokes flow that we have just discussed, you guys have covered that in your fluid mechanics. 211, 331, 231. Now we'll be looking at. Now we are switching to particles in the fluid, and we are going to look at three fundamental problems. Rigid sphere in rotational flow at low Reynolds number, rigid sphere in uniform flow at low Reynolds number, that to some extent you guys have already looked at, and rigid sphere in extensional flow again at low Reynolds number. All these terms are important here: rigidity of the particle, low Reynolds number flow, and these three different kind of external flows. So particle in uniform flow, particle in rotational flow, and third is particle in a, let's say, a simple shear flow that is easy for you to imagine. So if I'm suspending a particle in uniform flow, so let's say I'm generating uniform flow what is happening to the particle in front of me?
Momentum can be transferred to the particle.
Sorry?
Momentum can be transferred to the particle.
Momentum is transferred, and what will happen to the particle? Let's say I'm generating a low Reynolds number, which anyway for a PM 2.5 particle, if you'll calculate rho dV by mu, वो लो ही आएगा.
If we are generating a uniform flow, then it will just keep on moving in the direction of flow.
Okay. No force will be acting on it. Or force will be. Let's say there's no G, it's just me generating a flow, a low Reynolds number flow there. What is going to happen to the particles? Guys, again, 12th class की physics का question है ये.
Force will act on the state.
Sorry?
Force will act on the state.
Force will act, but since it's a low Reynolds number flow, and let's say I'm able to generate a uniform flow, what will happen? The particle will almost instantaneously attain the velocity that I have generated, attain the uniform flow velocity, and then force. Why is force in this problem of your particle settling? In viscous fluid, why is there force acting on the particle? The force 6 pi mu RV that we have calculated in the past. Why is that force acting on the particle? Why is the force acting? So here I am claiming in the example that I just gave that if I am generating uniform flow, then particle is going to reach, is going to attain that uniform flow velocity and will be moving with the fluid. Okay? But no force will be acting on the particle anymore. So if I place a particle in uniform flow, the particle, let's say uniform flow velocity is u, the particle will also be moving with the uniform flow velocity u. And no force will be acting on the particle, essentially because it's moving with the same velocity, relative velocity between the fluid and the particle is zero. When I'm standing stationary here, is there any force acting on me? Gravity. ठीक है, gravity act कर रही है और equal and opposite force from the ground is keeping me stationary. Any other force? You know the velocity with which, sorry? मतलब let's say हवा नहीं चल रही है.
Centripetal force due to
Centripetal force. I mean, more importantly, centripetal force एक next level होगी. I am actually moving at a velocity equal to what is the omega of Earth. So one rotation in 24 hours. And one rotation is 2 pi by 24 hours. So that kind of omega, if you look at velocity, omega times r of Earth is about 3600 kilometers. 3600 kilometers. 6400 kilometers. So for 3200. 3200 kilometer times 2 pi by 24 hours. Guys, ठीक है, वो इतना important नहीं है. So 22 pi by 24 hours into 3200 kilometers. This is the velocity with which I am here. Still, there is almost no force acting on me. Essentially, because the rest of the room or the rest of the atmosphere around me is also moving with the same velocity. So, relative velocity between me and the fluid around me is zero. as a result, none of us is experiencing any force in this fluid, although we are all moving. Same way, this particle in uniform flow, or if I'm generating a uniform flow here, the particles here are going to instantaneously attain that uniform flow velocity, and then no force will be acting between the particle and the fluid. Are we on the same page? Alright, force was acting on that particle because it is moving with some velocity, whereas the fluid at large is stationary. There is relative motion. It's only and only because of relative motion between the particle and the fluid that a finite force is acting between. Okay. So I was discussing that essentially to let you guys understand that here when I'm saying that a particle in uniform flow has force acting on it, this is a stationary particle, and for me to make this particle stationary, I have to apply an external force on it. वहाँ पे वो external force mg लगा रहा है. यहाँ पे if I'm saying, let's say I have a stationary particle in uniform flow, and you guys are interested in finding what the force is. That force is essentially the external force that I have to apply in order to keep it stationary. Or 6 pi mu r v is the force acting on the particle, and I have to apply equal and opposite force externally on this particle to keep it stationary. Same goes for rigid spherical particle in rotating fluid. There also, if it's free to rotate, it will essentially rotate with the angular velocity of the fluid. Okay, and again, no torque will be acting on it. Make sense? Now, for me to estimate, if I keep this particle stationary, we can estimate the external torque acting on the particle, or the torque that is acting on the particle due to the fluid, and external torque has to be equal and opposite to keep it stationary. Case 1, we have a force acting on the particle. Case 2, a torque acting on the particle. Case 3 is slightly more involved and more interesting. You guys have been talking about, so if I have water and let's say I add particles, again chalk powder in that fluid, viscosity of which fluid is going to be high, this pure water without any particles or the suspension containing particles? Kyun?
Since there are particles dispersed in the fluid, at the surface there is being mostly bounded.
Let's say surface की बात नहीं करते. अच्छा, particle के surface पे.
Yes.
Okay.
And that generates to a resistance to the motion of fluid around it, and that leads to the increase in viscosity.
एक second. So no slip boundary condition, when this particle is in uniform flow, no slip boundary condition is followed here also. It's just that no slip boundary condition means whatever velocity of the particle is, same as the velocity of the fluid. So there is really no, in this case, particle is not causing any resistance to the fluid.
Sir, can you repeat the situation with the suspension?
So, simple problem, I take a bottle of water, transparently now. I take two bottles of water, like this. In one, I add powdered chalk, in other, I don't do that. And I'm asking which one of those fluids will have higher viscosity. And from intuition, as you guys answered, and it's the right answer, that viscosity of the suspension is going to be higher. And my question is why? Why a powdered a suspension containing particles will have higher viscosity than compared to a fluid without particles? Yeah.
So the fact that most economic condition is followed in a uniform flow will be true, but only because it is a uniform flow. When we suspend some water, let us say chalk water and water, it is not necessary that the water is moving uniformly. So then the fact that was repeated, if there is flow around the particle, no slip boundary condition will lead to more resistance to the motion unit.
Right, and I just want you guys to, before I go into that deeper, what is viscosity?
Measure of fluids resistance to its deformation.
The measure of fluids resistance to its deformation, and rigid particles do not deform. Okay, I mean, if you consider this hand to be rigid, I mean, it's not exactly rigid. It's free to rotate, or this bottle free to rotate. It's free to translate. There's no resistance. And why is this happening, even though it's rigid? There's no relative motion between any 2 points. ऐसे जा रहा है तब भी, ऐसे हो रहा है तो भी. So in the case of fluid, or for that matter, for solid, if I try to compress it, it's going to resist that. And that's essentially because I'm creating some relative motion between any 2 points when I'm compressing or extending it. For the case of fluid, it's only and only in cases when it's getting deformed, and by deformation I mean when there is any relative motion between any 2 volumes of the fluid, only then viscosity is going to appear. In uniform flow, again, there is no, if I generate a uniform flow in a system once, it can continue in that state forever and ever. Of course, I mean, there have to, if let's say, if there are 2 plates and I start moving them with constant velocity, the fluid inside it is always going to continue to move in uniform flow. Viscosity, it doesn't really matter उसके बाद तुम glycerol को move कर रहे हो या water को move कर रहे हो, because viscosity will not come into picture because there is no relative motion between any 2 points in the fluid. So this idea of viscosity is, does it make sense? Now coming back to the response that he, can you tell me your name? Hanji? Snigdh, sorry. So Snigdh, the answer that Snigdh gave, that in the moment I'm talking about kiski viscosity ज़्यादा होगी, I'm not talking about uniform flow. Uniform flow में you really can't measure viscosity. That the fluid flow may not be uniform, as a result of which there is a resistance due to the low slip boundary condition, and that could be leading to higher viscosity compared to viscosity for the fluid without any particles. And when we'll be looking at this problem, particle in simple shear flow, we are going to see that net force, net torque acting on the particle is 0. It's free to move. When I am suspending particles in my fluid and measuring viscosity, the particles are free to move. I am not applying any external force or any external torque. They are free to move, free to rotate. And we'll see that even in the case when there is no external force or torque acting on the particles, it is going to resist the motion of the fluid. Fluid is paying a penalty of viscosity when I'm deforming it. Rigid particle, you cannot deform it. As a result, deforming this fluid containing particles is going to be costlier, or the viscosity is going to be higher. Effective viscosity of this suspension is going to be higher. qualitatively, does it make sense? Quick question, although please feel free to ask. Any questions, guys? Why are we now the fluid? Now you can say, sir, जो आप motion यहाँ create कर रहे हो इस bottle में, is that represented by any of these three flows that you are showing here? So how is this compared to that? Any response?
Closest approximation to when we are taking the water, closest approximation is there is stress like that, but not exact.
We'll go into the details of how to calculate force, torque or stresslet. At the end of the day, all you need to do is calculate the disturbance field created due to the particles in these three cases. Based on that disturbance field, you calculate the stress acting on the particle. Newton's law of viscosity will be applicable to estimate stress acting on the particle. And based on those stresses, integration over the particle will give you net force. First movement will give you the net torque. And again, first movement, when it's a vector product, it will give you stresslet. ठीक है, अभी इसका ज़्यादा चिंता करने वाली बात नहीं है इसमें. Coming to this point of why are we just focusing on these three kind of flows, when you can imagine that there are like infinite kind of flows that one could be generating. Why only three? So let's see. How's so I have 2 points in the fluid, one at x, another at x naught. And how's fluid velocity at x related to x naught? Let's say if x and x naught are close enough, or I mean when they are not close enough, you can think of a Taylor series expansion with n number of terms. The velocity of x you can denote as velocity of x naught at x naught plus first gradient plus second gradient plus third gradient plus fourth gradient and n number of terms. If x and x naught are close enough, you can neglect everything on the right hand side except the first gradient. Okay? Now, the first gradient one can write as sum of first gradient plus first gradient transpose plus first gradient minus first gradient transpose. मतलब ये एक तरह से still it's the same term. And we call the first term here del V plus del V transpose as E or strain tensor, and the second term del V minus del V transpose as the rate of rotation. So finally, I am claiming that to the leading order I can represent any velocity field as a summation of uniform flow plus rotational flow plus first gradient velocity. Okay? Uniform, the first term on the left hand side is uniform. अगर बाकी सब zero है, so we are talking about uniform flow. The second term has two components. One is pure straining fluid flow. Second is your rotational flow. Okay, so I'm essentially showing you that any flow that I'm generating, अब ये कितना ही complicated flow at macro scale, if I have particles suspended in this fluid, around that particle, I can, to the leading order, I could be representing external fluid flow as uniform flow plus rotational flow plus simple shear flow. Or simple shear flow alone, because simple shear flow has both rotational plus the gradient term or strain term. Am I making sense, guys?
Sir, that mathematical question was not understandable.
क्या था
The
mathematical?
transpose image.
You guys haven't looked at del V plus del V transpose and del V minus del V transpose. For any velocity field, if we do this, this is going to be a pure rotational flow and this is going to be pure strain flow. Tutorial में question होगा वैसे, but I think if fluid mechanics में भी there's a good chance you guys must have looked at it. नहीं? सोमनाथ सर taught you? ठीक है, ट्यूट में एक प्रॉब्लम पे हम काम करेंगे. Question, guys? So what you were saying, yes, this is a pure second shear flow is actually a summation of rotational plus extensional flow. Ideally I should have had uniform flow, rotational flow and extensional flow. लेकिन extensional flow थोड़ा सा unrealistic है. It's not something that is usually seen. Simple shear flow, which has this extensional component plus rotational component, I'm looking at that. And this is the only flow in these three kind of flows where there is relative motion between the fluid, any two volumes of fluid. So this is showing fluid going like this. So these 2 points in the fluid, there is a relative motion. These 2 points in the fluid, there is a relative motion. This is going to go faster, this is slow. Here and here, there is no relative motion. My body is moving like that. Uniform flow, rotational flow. I cannot move in simple shear. Make sense? Now let's look at by solving these three sphere problems, we are essentially interested in understanding the impact of particles present in a fluid on the fluid flow or fluid dynamics. So let's look at the first problem where your particle is in uniform flow. It's a stationary particle. When it's stationary, only then it's going to cause it's going to lead to any disturbance field in the fluid. Otherwise, it will just move with the fluid. कोई disturbance नहीं होगी. A particle, a rigid particle, can move with uniform flow velocity. And now let's look at some analogies between Stokes flow and electrostats that you guys have mastered in class 12. In electrostats, so if I put a charged particle, a particle with charge Q here, it will lead to an electric field around this particle. It will lead to an electric potential. Okay. Now let's look at analogy between the fluid. In a fluid is stationary, and if I apply a force F, so this fluid, let's say, is stationary. Now if I apply a force F, what is going to happen? No slip boundary condition is going to be followed, right? So the fluid around my hand is going to start moving with the velocity, with whatever velocity that I am punching, and that will create some disturbance field. Of course, when the fluid here is moving in this direction, the other fluid is going to come and replace it. So it's going to create a disturbance field. I'm disturbing this fluid is stationary, I'm disturbing this fluid now. So velocity field is going to be generated. Okay. So like in the case of electrostats, when I'm placing a charged particle Q, it's going to generate an electric field or an electric potential. Same way, if I'm exerting a force F in a fluid, that will generate a velocity field. So force is analogous to charge and velocity field is analogous to electric potential. Now, for the case of electrostats, we know how your potential is going to look for a charge Q. Right? Q by 4 pi r, 4 pi epsilon r is the potential generated due to a charge Q. Okay? We are interested in asking a similar question. How's velocity if I am exerting a force F in my fluid? How is velocity going to look like? And I am going to use your results from cll331, where you guys estimated drag force acting on the particle by solving for Stokes equation around that particle. मैं उसके results use करूँगा in order to get how velocity is going to look for a force being exerted, for a point force being exerted in the fluid. So point charge, the potential is going to look like this. Point force, how the velocity is going to look like. We are going to find that in a bit. I just want to show you, so Poisson equation here, again it's a linear equation and Stokes equation is something similar. Except when we talk about charge and potential, these are scalar quantities. When we talk about velocity and force, these are vector quantity. Electric field is vector in electrostats. Same way stress is tensor in fluid mechanics. Velocity, force, vectors, charge, potential, scalar, stress, tensor, electric field, vector. And we'll see that in Stokes law also we can write velocity as a function of force, the way we can write potential as a function of charge in electrostats. Alright, so some revision, what you guys did in cll231. So you have a rigid spherical particle in fluid. Either the particle is settling due to external force mg, or your particle is stationary and fluid is moving with a uniform velocity u. ठीक है, तो तुम लोगों ने ये सॉल्व किया था, and you did this by, so you have two equations, two variables, and all you need is boundary condition. Boundary condition on the surface, no slip boundary condition. When the particle is going with the velocity u, on the surface velocity is going to be u. Far away from this particle, velocity is 0. And what you are solving, again, the velocity u there is the velocity, the solution for this equation will tell you velocity in the fluid phase. Okay? You are not solving this equation for this part. This equation is only and only for the fluid. This particle is only providing you boundary conditions. And this is the solution that you got. It might look a bit more complicated than what you guys might have seen in your cll231, but वहाँ पे हो सकता है scalar form में लिखा हो, यहाँ पे I just written it in vector form. So ui is the velocity field. Again, ui is the velocity field in the fluid, and p is the pressure, velocity and pressure field generated in a stagnant fluid due to the motion of a rigid spherical particle moving with a constant velocity. uj.
Delta ij the Dirac delta function.
Yeah. It's a tensor. Alright, so now we already know what the force acting on, and you actually derive this force by calculating the stresses acting on the particle and integrating over the surface. Okay, so we know what that force is. That force is 6 pi mu r du. Substituting that in the above equation, so essentially replacing uj with fj, we end up with this. So ui is equal to fj. Algebraic substitution है ये. The top equation you guys got it by solving Stokes' equation theoretically with the appropriate boundary conditions. Okay, now all I've done is substituted the force expression in this equation algebraically, and we are left with this equation. Okay, and this is Fj is the force, net force acting on the particle. We are interested in finding out what will be the disturbance field generated by point force. So instead of this particle being, so this is a particle of finite size r, which is exerting a force F, or exerting a force 6 pi mu rv on the fluid, and this is the disturbance field that we are getting out of it. Now let's say I shrink this particle and make it a point particle. Point particle का क्या मतलब है?
Radius.
और capital R is much less than small r. Again, relatively speaking, size of this particle is much smaller than the position in which I am interested in finding out what the disturbance field is going to be. तो उसके लिए क्या कर सकते हैं हम लोग? So capital R is only in this term, and when capital R by small r is much less than 1, we can neglect this entire term compared to the term on the first term on the right hand side. Okay, coming back to the question that we were asking, how is U associated with F? How is the disturbance field associated with this point force that I am exerting in the fluid? How potential is associated with this point charge that I placed, that's given by this expression. Same way now, when we apply this boundary condition capital, so I don't know if this is still discussed in lecture 33-34. The time when Professor Jyoti Parani used to teach it, I had checked with her. This was cll331 lecture 33-34. Nowadays I don't know in which lecture you are speaking.
It has not been covered last.
Sorry?
It has not been covered in the last course.
Drag force acting on the particle derived हुआ है.
ड्रैग फोर्स कवर हुआ था, बट यूआई एंड इसका डेरिवेशन नहीं हुआ था.
Drag force कैसे निकालना?
सर ड्रैग फोर्स जस्ट काइंड ऑफ एक लेक्चर का था जिसमें सिंपल बॉडीज थे एंड फॉर्मूले यूज करके बस निकालना था.
हाँ, मतलब 6 pi mu r v इस सॉल्यूशन के बिना नहीं निकलेगा. जो टॉप पे सॉल्यूशन है उसके बिना, मतलब उससे ही 6 pi mu r v निकलता है. वो भी
नहीं हुआ.
ठीक है, I'll share some notes with you that you guys can look at.
And sir, I have one doubt. Why did you take Dirac delta in the original equation that is started with?
ये solution है अपने Stokes equation.
No, in the original equation that 2 slides back.
Here I didn't take any direct delta.
No, 2 slides back.
This? इससे पहले नहीं.
This one. Minus and delta.
अच्छा, so here I'm point force. Point force is here. This is delta function. Sorry, this is delta function. जो point force at r, it's going to be 1. Otherwise, it's 0. This delta ij is not that delta.
Okay. It's just my doubt that.
नहीं वो बस point force के लिए. So my charge is a point charge for which this is the potential. Question is, if I have a point force acting somewhere, what will be the velocity field? And you essentially have to solve this problem. Alright guys, we'll continue from here in the next class. When we have capital R and small r going to 0, we'll end up with this expression. We'll continue from here in the next class. Guys, in the from the next class after 9:10, I would request you not to enter the class.